In the previous section, numbered as 4.1, we saw that the derivative can be used to determine when a graph is increasing or decreasing. Now, we would like to see what the second derivative, which is the derivative of derivative, can tell us about the shape of a graph. By considering the two functions, f of x equals x squared and f of x equals minus x squared, I will try to explore this situation. I mean, the first derivative of the f of x, let's say this is g. Okay, maybe you can confuse. This is g of x. So first derivative of the f is 2x. And the second derivative of the f is 2. So we know the graph of the x squared function. This is the x squared graph. So as you see, the graph of the x squared is second derivative of the... So the graph of the x squared is go up, and actually not go up. This shape is called a concave up, okay? So here, derivative of f is increasing. Why? Because second derivative is positive, so derivative of f is increasing. So here it is some negative value, so it is bigger than the previous value, bigger than that value. So here it became a 0, and again it continued to increase, being a positive, and go to the infinity. So f prime is always increasing. This shape is called a concave up. Concave upwards. Okay, so when the second derivative is positive, the shape is concave upward. So when the second derivative is negative here, minus 2x first derivative, second derivative is minus 2. So as you see, that is less than 0. So the graph of the minus x squared is this one. So now the f prime derivative of the f is here positive, comes from the positive infinity, positive, and this is 0. Why this is positive? Because this is narrow angle, but here it is wide angle, so it is negative, and it goes to the minus infinity. So in that case, we say this graph concave downward. So by using these observations, we can generalize that fact, okay, as a concavity. Let's give a definition of the concavity. So the graph of a function f is concave upward. The graph of a function f is concave upward on the interval AB if f prime is increasing on the same interval, or this is concave downward. F graph of f is concave downward on the interval AB again if f prime is decreasing. Okay, this is the definition of the concavity. Geometrically, the graph is concave upward. This is a concave upward. The graph is concave upward on some interval AB if it lies above the tangent line. Okay, these are tangent line. So this graph lies above the tangent line, and the graph is concave downward on some interval AB if the graph lies below it is tangent line, like this situation. Okay, geometrically we can make this comment. The important question is, how can we determine when f prime x is increasing or decreasing? Actually, we know from the first derivative test. So if second derivative is negative, f prime is positive, f prime is increasing. If second derivative is negative, f prime is increasing. Actually, if you consider f prime as a g, you can decide easily, or h, let's say. For example, this is h of x. So this is h prime of x. So when h prime is positive, okay, so here when h prime is positive, this is the second derivative of the f. It is increasing, so this is concave upward. When h prime is negative, which is second derivative of the f, so f is concave downward. By this way, I defined a new notation for the second derivative actually for you. So f double prime means is the second derivative, okay? Second derivative of it. Actually, it is derivative of the derivative f prime of f prime, okay? By using Lipschitz notation, we can write this is derivative of the f prime. Okay, so sometimes we use this notation, d square of f of x over dx square, or d square y if f of x is not by the y, dx square, or y double prime can be used as a notation of the second derivative. As a summary, I can say that second derivative of the f of x, if this is positive, f prime of x is increasing, okay, like this one. So graph of the f of x concave up. So the graph like this one, either this graph or that graph. If this is negative, f prime is decreasing, so f is concave down. So the graph like either this one or that one, okay? In addition to concavity, I can say something here. In these two cases, this is, for the first row, this is concave up, this is concave up, okay? But in the first case, this is decreasing. So this is decreasing concave up, this is increasing concave up, okay? And in the concave down case, this is increasing, this is decreasing. So this is increasing concave down, this is decreasing concave down. So maybe briefly I can say here, second derivative is positive, but not that case, sorry. We should write here, second derivative is positive, first derivative is negative because it is decreasing. Second derivative is positive, first derivative is positive. In the third case, second derivative is negative concave down, first derivative is positive because it is increasing. Second derivative is tan 0 because it is concave down, first derivative is negative because the function is decreasing. In this section, we have a new definition. Actually, the point where the concavity change is called the inflection point. Okay, so let's write the point where the graph of a function change is continuous. First of all, it has to be continuous, and the concavity of the graph changes. This point is called an inflection point. I mean, for example, concave down. After this point, it starts to concave up. So this is inflection point. Okay. For example, concave up changed to concave down. So this is inflection point. Concave up increasing. Here concave up increasing. Concave down increasing. Concave up increasing. So concave down decreasing. Let's look. Concave down decreasing, and concave up decreasing. Again, this is inflection point. Here concave up increasing, so concave up decreasing, and concave down decreasing. This is again inflection point. Sometimes it's possible change the increasing or decreasing. For example, concave up increasing, concave down increasing, concave up decreasing, for example. Again, it is inflection point, okay? So for example, concave up increasing, concave down, so again concave up, so it's not inflection point, okay? Not an inflection point. This is concave up. This is also concave up, okay? So it's not an inflection point. So the point where the concavity change called the inflection point. In this section also we talk about the curve sketching, but I would like to give separately this part. Before giving the curve sketching, maybe I can talk about testing for inflection point. So how we can find the inflection point, and then we can complete this part of the record. Inflection point. The first step, okay, let's write step 1. Find all partition numbers of not f prime numbers, let's say C, f double prime. For f double prime, you should find the all partition number, okay? But here, such that f is continuous at x equals C. And second step, for each of these partition numbers C, construct a sign chart of f double prime, okay? So construct a sign chart of f double prime, okay? Near the such x, near each x equals C. And step 3, if the sign chart of f double prime change sign at C, then C of FC is an inflection point, okay? If the sign of f double prime changes at this point C, okay, then C comma f of C is an inflection point of f, not f double prime, inflection point of f, okay? If the sign chart does not change sign at the C, then there is no inflection point x equals C.